Greetings, statistics scholars, and welcome to this first video from chapter number 2. In chapter number 1, as we explored the collection of data, we learned about two major types of variables: quantitative variables and categorical variables. In videos 2 and 3 of this series from chapter 2, we'll explore quantitative variables in greater depth. In this video here, the first video from chapter number 2, we're going to take a closer look at section 2.1, which deals with categorical variables. You see here on this slide a roster of the population of all 11 infielders who played with the Pittsburgh Pirates in 2019. We see that we have 4 columns in the center of the table that tell us the height, the weight of the players, as well as which side of the plate they batted on, and which arm they used to throw. Of those 4 variables, which would you say were categorical variables? Height and weight are quantitative variables. We can do arithmetic on them. For example, we could ask, what's the difference between the tallest height of a Pirate infielder and the shortest height? We could subtract. Or we could add all the weights together and divide by 11 and find the average weight. Height and weight are quantitative variables. But the variables throws and bats are categorical. We wouldn't do arithmetic with values like right and left and both. So if you said throws and bats, you were correct. Now, of those 2 categorical variables here, the throws variable is not particularly interesting, at least for the Pirate infielders, because they all throw using the same arm. But the bats categorical variable is a little bit more interesting. We noticed that there were 2 Pirate batters, Josh Bell and Cole Tucker, who batted from both sides of the plate. If we look for those who fell into the left category, we see that there were 4 of them: Adam Frazier, Corbin Joseph, Kevin Kramer, and Colin Moran. And we also can see that there were 5 Pirate infielders out of the 11 who batted from the right side of the plate exclusively. What if we wanted to try to summarize those findings? One way to do that would be to make something that we call a frequency distribution table. Notice here that what we've done is in one column we've listed the possible values for the bats categorical variable, which are both and left and right. And then in another column we've listed the frequency, or the count, of the number of cases that had that particular value. Frequency distribution tables are a very common and very useful way of summarizing information about a categorical variable and the values it can take. Now, once we start talking about the counts or the frequencies of different categories of a categorical variable, an important vocabulary word that we like to talk about is what we call proportion. If you divide the frequency of a category by the total number of cases, you'll get what we call the relative frequency, or the proportion of that category. So, for example, suppose we were interested in the proportion of Pirate infielders who batted from both sides of the plate. There were 2 of them out of 11. So we would say that that proportion was 2 11ths. Now, in terms of symbolism, we're going to use the letter P to denote a population proportion. Remember here that these 11 were the only infielders who played with the Pirates in 2019. So if I wanted to talk about the proportion of 2019 Pirate infielders who batted left-hand, that proportion, which is 4 11ths, we would write that as P equal to 4 11ths, because that is the population proportion. So remember that symbolism. P stands for a population proportion. Let's look at an example now that refers to a sample. This is a study that was done in the late 1970s having to do with patients who had Hodgkin's disease, which is a type of cancer of the lymph nodes. And in this study, they looked at a sample of 538 different patients. And we have what's called here a two-way table for giving information about these 538 cases. It's a two-way table because for all 538 cases, there were two quantitative variables that were recorded in this two-way table. The first of those categorical variables was the histological type of the patient. Each one of these patients with Hodgkin's disease had one particular form of that disease. Some had what was called lymphocyte predominance, which is indicated by the code LP. Some had nodular sclerosis, indicated by the code NS. Some had mixed cellularity, indicated by the code MC. And some had lymphocyte depletion, indicated by the code LD. Notice 4 different categories of histological type. That was one of the variables that was recorded for each one of the patients. But there was another variable as well, a second categorical variable, their response to treatment. How well were they doing after 3 months of treatment? Did they have a positive response to the treatment? Did they have a partially positive response? Or did they have no good response at all? Each one of the patients fell into one of these 3 categories as well. And what our two-way table does is it tells us how many of the cases had particular combinations. So for example, if we look at that number 16 that's right in the center of the table, that's in the NS row and in the partial column. What that's telling us is out of the 538 patients, there were 16 who had nodular sclerosis who had a partially positive response. The 154 number that you see in the table in the positive column refers to the fact that there were 154 individuals who had mixed cellularity as their histological type and who also had a positive response to treatment. So this two-way table gives us a nice way of summarizing the frequencies for individuals that had a particular pair of values for these 2 categorical variables. Now, if we have a two-way table like this, or really any situation with categorical data, we might ask how we might visualize the distribution of these variables. How could we visualize the distribution of histological types? Or for a given histological type, how might we visualize the distribution of possible responses? The answer to that is something that's probably pretty familiar to you, and that's to use a bar graph. Bar graphs are often used to help visualize categorical data. So, for example, if we wanted to show visually what the breakdown of patients was according to histological type, we could make this bar graph. On the horizontal, we'll list the 4 different categories for histological type, LP, NS, MC, and LD. And then on the vertical, we'll indicate the frequency. So the height of the bar will tell us how many of the cases fell into each one of the categories. And we can see very clearly from this visualization that by far the most common histological type was the MC type with 266 individuals. We can also see at a glance what the least common type was, LD with 72. Now, as another example, suppose we wanted to kind of break down those 96 patients who had the NS code according to their responses to treatment. We can make another bar graph. Here, in this particular case, on the horizontal, we've shown the different possible responses, positive, partial, and none. And again, on the vertical axis represents the frequency. So the height of the bar is telling us how many positive partial, and none responses did we have out of those 96 individuals who were in the NS category? Bar graphs are by far one of the most common ways that we have for visualizing information about one or more categorical variables in a particular study. We have some further terminology or symbolism that we want to introduce now. In this particular situation, remember that we weren't dealing with a population. These 538 cases were not all of the folks with Hodgkin's lymphoma. They were simply the ones in this particular study. Whenever we have a sample that we're working with, and we want to tell people that the proportion is coming from a sample rather than a population, we put a little hat above the P. So P hat denotes a sample proportion that have a certain property. So for example, if we were interested in expressing the sample proportion of patients with lymphocyte predominance, we see that there were 104 out of 538 in all. So P hat is 104 divided by 538. Now that's the symbolism that we use if we want to talk about just one sample proportion. But as a final note, we want to talk about the fact that sometimes we like to use subscripts to help distinguish between proportions that are coming from different groups. Remember here that we had 4 subgroups corresponding to the different histological types. Suppose that we were wanting to refer to the proportions of patients from each of the 4 types who had no response to treatment. If we wanted to do that, we could use the following symbolism. I could say P hat sub LP equals 12 out of 104, because there were 12 out of 104 of those in the LP category who had no response. I could say that P hat sub NS was 12 over 96, because we can see from the chart that there were 12 out of 96 of the individuals in the NS category who had no response, and so on and so forth. This is a very common strategy that we'll use going forward. Sometimes we want to talk about a sample proportion or a proportion that come from a particular group. And a good way to do that is to put a subscript after the letter to indicate which particular group we're talking about. You'll see this symbolism a lot going forward in your textbook. I hope you found this to be instructive and useful as you're moving forward in your learning with section 12.1.